All right. We're live for the finale of Avanaka 2025, which drops in about 50 minutes. Now, we're still missing the star. And I'm going to do what other people have done and import a solver. Now, I think I have a method. I think I can do this without even using Gaussian elimination, just with substitution. But I'm not confident enough in that to get that done by midnight. So we're going to figure out how to use Optimus. I've already taken a look at the documentation a bit. So this here is a wrapper over various other solvers. And it looks pretty easy to use. So I'm just going to add that as a dependency. We'll just copy this. And let's just put this dependency in along with everything else. I don't think I'm even using that. I think that's a default dependency. Alrighty. And let's do this in a separate file. I want to keep this. So day 10 with a solver. Now I'm just focused on part 2 here. So I think I can delete all this other code and delete the parsing that's relevant to part 1. And then I don't need to have it parse into binary either. In fact, we won't even bother with a case class. We just want joltages and buttons. In fact, I might just parse it as is. So tuple, you know what? We'll actually just keep the case class. We'll keep the case class. We'll remove this goal here. And let's work with that for now. It might actually be fine. No. We're going to make this a list of vectors of int to match the size of the joltages vector. Okay. So we can take this out. Buttons up, split the two list. Okay. And then for each of these, what was I doing this from? Okay, so we're just parsing the inner slice and separating with commas. And then these are the button ones. And then we're making a string from that. But instead, I think we just want to keep the numbers. So this is a set of integers. Let me fix this music real quick. I think we just want that to be the vector, right? So we'll just make this 2 vector. What is this? Hey, Alex, how's it going? I'm going to use a library for day 10 part 2. So I'm just revisiting that to try and get done by midnight. I do think I have an approach that's mostly just using substitution that can narrow down the range enough to brute force. But I'm not sure yet. I've just been solving a lot of these by hand, and it seems like you can do it pretty simply there. And you could also do like some smarter pre-processing to make them simpler. But basically, brute force after some substitutions, I think would do the trick. But I don't feel confident enough to do that by midnight. So we're using a solver. I think I kind of wanted this to be a vector matching, but yeah, it can just be a set. So let me make this a set event. And we can take out this goal int. So we're completely ignoring part 1 here. Okay. Now, what are my imports? Okay. We'll import this, and now I know there are vars. So for each machine, let's move our imports up. So we'll define a solve, and this will give us an int, and we take our buttons. So each button needs to be its own variable. So I'll do buttons.zip with, and we'll just name them all. So we'll name them from like A to Z. Zip with A to Z. Map. So optimization dot. I don't think we need this. We'll do model dot int var. Is there an int var in there? MP. It should be imported. Give me a sec here. Let's make sure it's actually imported. Okay, these imports are not being found. So metals restart the recompile workspace. Oh, we missed a comma here in the build file. I see. Okay, now we can import the changes. Now, I wish there was an API doc for this. Nope. I mean, I guess we can just go through the source, but we can also browse around in here once this loads up. So basically, we have our vars, val vars equals whatever we do there. And for each variable is associate. Well, for each joltage, we can make an expression. So joltages.map and an expression would be, let's see, we just find all the buttons. So vars.filter that all the buttons that match the index of this J. So I'm going to zip this with index, joltages.zip with index.map. So we have J and I. And then vars.filter. So something along the lines of contains I, right? And then we'll do something along the lines of build an expression that says that's equal to J. And then we'll want to minimize those variables given each of these constraints. Okay, is this running now? Yes, this is running now. Great. So let's give this a shot. Model dot int. There's an int var in there somewhere. No. Oh, we need to have a model in scope. Okay. So we'll define a model out here, and we'll use an implicit given model. We can define the model later. So given a, or using rather, using an NP model, now we're going to do model dot NP font. Okay, maybe let's try importing it directly. Model dot MP var. Okay, I don't know why I couldn't import that this way. So we have an MP var. The main, so there's the range. MP int var. We want a symbol too, though, so we'll use this definition. So given the label, so the name and I don't know. Well, so this is the button itself, the button, and the letter or the label. We're gonna make an MP int var with that label. Label, and then the range. So the range of values for any given expression. Here's one where we're doing this by hand. All right. So it's going to be the joltage referenced that is the smallest, right? So B appears in these two lines, and we'll get the smallest. Okay, so B appears in these two lines specifically because it increments all three of these. So joltages dot filter B dot contains. Well, let's calculate this separately. So max value B can have. It's gonna be joltage dot filter B dot contains, and then it's gonna be the minimum of those. And this is non-negative, so we have 0 to max as our range. Cool. Great. Well, now that we have variables, buttoned. What's wrong with this zip with? Oh, wait, just zip. Zip. And label? Required a string. Okay, L.toString, string, sure. Okay. And we could print those. We'll try it when we're testing this out later. So now we take all of our joltages, and for each of those, if a var right, so we're going to filter through the vars. I think the vars needs more information. So we want basically the vars kind of zipped with the button that they are referencing. So let's do that. So the var will reference the button, and that whole thing will be a map. To map. Okay. And now we'll filter here. So in case there's a var, there's a button, and we want button.contains I. And from there, we make an expression. So expression or constraint. Let's look for it here. So dot constraint. Optimization dot, what else is there in here? There's an add. No, that uses constraints. We're trying to create a constraint. Subject to constraints. Okay, great, but we want to make a constraint. You know, let's just look at the definition of this. Look at the definition of constraint and what are things that extends that. Oh, we can straight up define a constraint. Optimus.algebra.constraint, left-hand side operator. So this is going to be like equals or something. Yeah, dot equal. Great. Right-hand side. Okay. So this is kind of exciting. Import optimus.algebra dot constraint. And now here we're making constraints. So constraint left-hand side is going to be an expression, which is going to be the sum. Vars filter. Why are we filtering the vars? We only want the vars that are associated with it. So wait, we should do that separately. So first we filter it by whether its set contains. And at that point, we don't need the button information, so we can turn this into a collect. So we're going to do vars collect case VB if B contains our button touches that index. Great, and in that case, we'll just keep the var. Okay. And I'll just call this values. Okay, and then now these, we need to make an expression. I imagine, okay, yeah, you can probably just do plus on the var. Okay, so let's do v's.reduce with blank plus blank. Does that work? Yep. Okay, and that is going to be a constraint, or the left-hand side of constraint. Great. And then now on the right side goes the voltage. So we have a constant. Oh wait, no. We need an equals. So let's go back to the constraint. What was that constraint relation? Where do we import algebra.constraint relation equals? Okay. So EQ, we can just do the import here. And then constant. No, I think we have to look this up again. So constraint, expression, constant. Oh, you can just straight up put in a number. No. What extends? Extends expression, term, constant. Okay. Oh, it is constant. Const. And value is a double. There's no int. Will this work? We'll try it out. So J. So these will be our constraints. So val constraints equals that. Great. Now we solve with, well, we're going to minimize. So model.minimize. Minimize. Okay. We're going to minimize the sum of all the vars. So vars, whoops. Vars.keys. And we make a sum. Let's do that separately. Val sum equals vars.keys dot reduce with plus. So we minimize the sum. Subject to, is that how that works? No. What was I seeing that subject to? Subject to constraints. Okay. And whoops. Oh, it's just inside optimization. Great. Oh, and This is a side effecting. Is it? And then we start. So we subject to those constraints and then we minimize right in here. But we need to start the thing. So do we start afterwards? So we start afterwards. So subject to constraints and and then we minimize some and then start. And then that returns a Boolean. How do we get the value? Oh, we get the value of something. So I guess we can get the value of sum. Let's do that. Sum dot value option double. So we're gonna map that to it. And that is our answer. Just throw a dot get on there. Okay. Let's see how that runs. What's going on here? Expression required np int var. Oh, right. This is gonna be like fold left, I suppose. Why did that work here? So these are just a collection of int vars, and we can reduce that with plus. This is also a collection of int vars, and we can't reduce it with found an expression. I guess if we want this whole thing to be an expression, then that won't work. Expression. Okay, yeah, given it that type hint helped. And this. Oh, this is a repeated parameter. Or we just put the star in there, right? Great. Now sum value is not a member of an expression. Sum dot I don't know, I suppose we could define a variable that's equal to that. Sure. np int np var, will that work? No, hold on. I don't want to try that. There should be a way to get this value out. So what's going on here? They choose a model. And here they're maximizing this expression. Okay, here we're minimizing an expression. And then add, what does add do? Add constraint. Okay, well, we've already added constraints. And then we start, and then we get that by taking our individual vars. Okay, so let's just do this sum.map a value. Right, if it's a var, we can get the value of it. dot sum. Wait, the sum is a whole expression. You can just do vars dot keys dot map value dot sum. What does it not like here? Oh, this is a double. Wait, this value is going to be an option of double. So let's flat map that. Dot sum dot to int. And let's just try that. Let's just try that. So we're going to do machines.map solve using, so we need to model np model, and we're just going to use the default. Is it default to something? Yeah. Okay. And then question asks, what's the sum of all of those? Yeah. So dot sum. There's an empty dot min. When are we doing dot min? Dot min. Okay, so if the button does not hit anything, that's weird. Why would the button not hit anything? It can just be joltages.max, I suppose. We can improve it if necessary. Okay. And there's an answer. But it's not the right answer. But we're on track. At least we've got something that's fast, right? Okay, let's try it on a single example. Turn to day 10. Let's switch to the example input. And let's just take one. Okay, and for that first one, the answer should be 10, right? So the first machine, wait, where is it? Oh, here we go. 10 button presses. And here we're getting 9. How are we getting 9? So let's print all the values then of all of these. So we're gonna do a tap each. And let's see. For each var, oh, these are the values. Sure, we'll just print line all the values for now. Okay, and there are 1, 2, 3, 4, 5, 6 variables. And we're only getting 4. Okay, so we screwed something up there. So we're zipping the buttons up with A through Z. Did we not get enough buttons? Yeah, let's just print each of those. So vars for each print line. Okay, so A is 3, F is 0 and 1. 0 and 1? No, oh, wait, those aren't in order. Sure. Let's not just print line. Let's do like a do list dot sorted for each print line. Uh, sort by rather, and we'll do the vars name. So one dot symbol. Okay, 3 1 3 2 2 3 0 2 and 0 1. So that much is correct. And then we have our constraints. Let me take a look at those too. So constraints for each print line. Oops. Okay. I can't quite read all of those. So, well, basically it's saying exit 5, exit 4. I don't know which one exit 5 and exit 4 is, but we do have that the joltage, the first joltage, only has, yeah, exit 5, index 5 and 4. So that would be these two. So that looks correct. And there are 4 constraints. So sums to 5, sums to 4, and sums to 7. Yeah, I think that looks right. 5 and 1. This is 3 and 2 and 4. So 2, 3, 4 all have 2. And this is 3, 1, and 0. So the first 2 and the fourth all have 3. Okay, so the constraints are each good. And let's get the values for each of those specifically. Or we did get all the values. 1, 0, 5, and 3. The first one wants, well, now let's get that. Let's print the actual values, variables along with their values. So instead of this tab each here, we're just going to expand this definition. So this flat map. So we have a var. And it has value, dot value. And that var has a label. So tap that. So value, we're going to print line. So the label, b dot symbol equals value. Okay. So A, the first, I want those sorted. So keys dot sort by symbol. Symbol? No. Wait, they should each have a symbol. Or is there not a sort by method? Okay, we'll do like a to list. Okay. Oh, wait, now we're getting the right answer because we did the sort. Weird. Huh. Hello there. Well, why don't we just try running that for everything then? We can turn off these print line statements. Well, let's try it first for the example. Everything in the example. We should get an answer of 33. Cool. And if I remove this sort by, then I don't. Oh, is it because it was a set? Was I mapping on a set? Keys isn't it? I don't know. It says iterable, but is that iterable a set? Key sets are iterable. Okay. Fine. It is the final night. And just in time, I have made my cheat for day 10, part 2. I don't know how much of this you caught. If you'd like a little tour, I can show you what I've done. So 16, 459. Too low. Maybe I've not cheated successfully. Okay. Well, now I need to find an example in which it's failing so that I can debug. Well, for one, I don't think this dot value should be failing. So we'll just change that to dot get and see if that doesn't fail. Okay, cool. We get the same answer. Yep, I'm using a solver, but it's given me the wrong answer. Hi there. Do I want a hint? Well, as far as like solving this correctly, I don't think I need any hints for like doing a different approach. But if you see what's wrong here with my code where I'm using the solver, I'd love your eyes there. I mean, I think I'm using it correctly. I'm modeling it correctly, right? So we did print off these constraints. They look correct. Modeling of the variables look correct. And using it worked out this way. Oh, integer overflow. You're right. You're right. That is a suspiciously small answer, I suppose. Yeah, that's great. Thank you. Ba, 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 ba. Where is our to int? You know, it's kind of annoying. I'm using int vars. I think those are probably fine because those are never going to be big, right? Well, actually, the maximum for each of these is going to be just the sum of all of the. I guess there are that many rows, huh? Okay, so we'll make this we'll make this a long. Well, no, we're not going to sum it first. Let's just make it, we'll get it, and then we'll do a too long here, and then we can sum it. And then here we are getting longs and we're summing those. I'm still getting the same answer though. So that wasn't it. And like if we were to take all the machines, map to voltages.sum, that is like the maximum possible number of button clicks, right? Yeah, for each of those. And you do the sum of all of those. This is an upper bound. So this is the largest possible answer, 65,000. So I don't think the long bit is an issue, unless somehow that map, not too long, dot sum. So this is an upper bound. Two is floor. Oh. Yeah, it should be floor. I mean, these should be integer solutions. Okay, this is a double. Let's do a round. Well, round too long. 65021. Like maybe there's one that's like slightly off. 16463. There it is. 16463. Good catch. Thank you. All right, our calendar is ready for day 12. Thank you. Good catch. Now overflow rounding. Good catch. All righty. Okay. I mean, so this library was nice to use. You make a variable, it has a label, and then you just give it a range, and you can just apply like a normal Scala range here. And then the constraints, you can build constraints simply by adding these together. So these are variables, we're adding them together. And you know what? I wonder if you could actually just use equals here. Like, is that a method that's built in? No. Constant dot equals. Yeah, there's no syntax for that. And those are pretty straightforward. But it does feel like cheating because the only real work I've done here is recognizing the system of equations. I'm not doing any of the manipulation myself. How to end up solving day 10? I like this. I used a solver. So here's the library I used. I'll just put in this documentation page in chat. And you know what? I might as well commit this too. So, all right. Solve 2025, day 10, part 2 with solver library. Thank you. Okay, and there's my alarm, which means we have 2 minutes left. By the way, my blog post is up for day 9. This is a blog post I wrote for the Scala Center. So let me pull that up. I'll drop that in chat for now, in case people are curious. I think I did a good job of simplifying it. So like that's all the code right there. And honestly, most of the work is done by just a few lines. The rest of it is just like models. And tomorrow we start doing FPGA. Should we start with it? I kind of want to start with Cinecore. Because I still need to choose a problem for FPGA. But that can be up to vote if everyone else wants to do FPGA too. Alrighty. There's an advent of FPGA that Jane Street puts on, a little contest. So you choose one of the problems of this year and you solve it in like a hardware description language. And they are pushing in particular, it's called Hard Camel. So it's like an OCaml DSL for hardware. Yep, that's the link right there. So it sounds like a fun project. I would be into it. Oh, let's make my new file. Well, D12 worksheet. Cool. Here we go. Day 12. Let's do it. Maybe. All right. Christmas tree farm. So we have a grid, I guess. Summary of your situation. First, it contains a list of the present shapes. Second, it contains the size of the region under each tree and a list of the numbers of presents of each shape that need to fit in that region. Okay, so this is a list of the present shapes. Ah, I see. Weird shaped presents. Oh boy, we need to like fit those together. Second, it contains the size of the region under each tree and a list of the number of presents that need to fit in that region. So like 4x4, and it needs two of this shape is what it's saying. Okay. Ah, this sounds tricky. Like I want to just brute force it and see if that works. I guess for any given shape or pair of shapes, you can figure out the most compact way to combine them. Okay, the first section lists the standard present shapes. For convenience, each shape starts with its index and a colon. Okay. Each line starts with the width and length of the region. The rest of the line describes the present that need to fit into the region by listing the quantity of each shape of present. Need to fit one present with shape index 0, yada yada. Presents can be rotated and flipped as necessary to make them fit in the available space, but they have to always be placed perfectly on the grid. They can't overlap. I also need to know how many of the regions can fit the presents listed. In the above example, there are 6 unique present shapes and 3 regions that need checking. So the first is 4x4. Okay, you can fit that. So you don't need to just find it. You need to determine if it's even possible. Which isn't great for the brute force story. That region, you need to try and fit one present with a shape index 0. Turns out that these presents can all fit in the region. Okay, so the shapes are 0, 3, and the last 2. So 0, 2, and the last 2. So for every pair, we could assemble all the possible shapes that we can make together. You're gonna nope out? Where's the solidarity? Well, I'm thinking I'm gonna take every possible combination of two presents and find like the minimum shape that those two can fit. And then maybe from there, the brute force story will be easier because I'll have sort of pre-computed part of it, the some shapes, and then we can try and jam those together. Yeesh. Well, part two should be a single click part, right? If it's like day 25 at all. But yeah, this year could be different. Hmm. And in the third region, there's no way to fit all the presents into this region. Okay, so I need to model a shape. And how I think I want to do that, I don't know, when it comes to grid problems, I don't like boundary checking and whatnot. I usually just do a set of points. So I can model a shape with a set of points, and then I can make some translation methods on that that basically move all the points. Yeah. And then I sort of brute force search on those translation methods. In another case, we'll probably need those translation methods. So you're watching me to find out. Well, you're also allowed to backseat here because I might get stuck. At some point, I should stop and make sure I brainstorm other ideas. I mean, how would you do this if you were? I guess you don't need to brute force every possible location. You could just take the boundaries of them and sort of move one down and like try to push it in. So if we had two presents, we kind of rotate them around each other, and as we rotate them, we kind of try and mash them together. Then we find like the minimum grids for that, and then we rotate the presents. So we try different rotations of the present and do the same thing. That's not too bad. Now, where that might be a dead end is what if in the broader puzzle that's that nice melding we found isn't the way it's going to meld in the real puzzle, right? Once you have three shapes, the optimal packing might not be locally optimal for any given two, right? I'm thinking it should work, but I don't know for sure that the optimal packing for three is going to contain within it the optimal packing for any two pairwise, right? I mean, we can draw things a little bit. So let's brainstorm on that. Okay, so roughly we could have three shapes. I'll make them yellow. Um, perp, 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 and maybe the best shape. So let's say the left-hand shape looks kind of like this, and the two right-hand shapes are like this and like this. Now, in this case, it happens that for this shape here, well, here's the thing. Maybe there's a gap of two here. If we were just taking these bottom two, then the optimal packing would be like that, right? For those two. If we're just to take the two on the right, the optimal packing would be like that. So yeah, the local minimum is not going to work there. So there goes that idea, but I'm glad we got rid of it. Um, yeah, so a greedy approach won't work. Thank you. But that leaves what? A brute force approach? We start with one, and then we find, um, how big are our shapes? Maybe it won't be so bad. Okay, these shapes aren't terrible. They all fit within 3 by 3. That's nice. So actually, maybe for this specific case, hmm. So certainly my example, I don't see that in here. But we could just add one after the other. But how deep could we go? Geez, some of these are huge. There's so many presents. So I guess in some of these, you kind of have to come up with optimal tilings of sorts, right? So maybe you have 35 of these, and maybe you can have an optimal tiling of that shape, but maybe the optimal tiling involves combining two shapes that are complementary. Dynamic profiling by profile, maybe. Um, yes. We could have a local cache, or of like local or like smaller problems. But the thing is, when it comes to tilings, I feel like I don't know, like you can tile 9 squares perfectly, but have have you seen the optimal packing of 17 squares in a larger square? So here's the thing about tiling. Um, the solution for 16 might be very different from the solution for 17. This is the best found tiling for 17. Deep, you think so? I don't know. This over here kind of makes me think DP wouldn't work. Well, I mean, I could write an algorithm and I could always just slap memo on it if it doesn't, if it's not fast enough, right? Yeah, I can write a brute force, try an example, prove that works, throw a memo, check that still works, and see if that holds up for the whole problem. Yeah, each can be encoded in 9 bits, I suppose. Mm. And then you encode all of its like shape rotations too. So then your rotations then are a map from one set of bits to another. That's an optimization I feel like I'd rather save for later. So I'm going to start with the set of points just so I can do my proof of concept. And we're going to have some methods to like translate it. So north is just going to be points.map, and for all of those, so import those dot, and then def s equals points.map s, etc. North, south, east, and west. Um, And then we have clockwise, def clockwise, points on map. Now, each of these, oh, I guess it depends on where everything. I guess I can center these. No. Yeah, so each of these are 3 by 3. So we choose, we have to find the center of that if we're rotating. This is Tetris. It's the worst Tetris problem we've received so far. Oh man, I thought we were going to get an easier problem than this. Like day 25 is usually a nice break, right? There are too many people complaining that it's been easy this season. I feel like we're all getting punished. Okay, clockwise. Well, I mean, we could just do clockwise around the origin, around 0, 0. Then when we parse these, we can do when we parse these, we can center them as we're parsing them. That way, when we're like enumerating, we can make them we can rotate them before we translate them right or left or something. Then we won't have to worry about them like rotating all the way around like an origin that's far away. Hmm. And I suppose we should just cache all of the rotations. Yeah, I think we'll cache all of the rotations actually. So we have a point, and you know what? I need a visual for this, otherwise I'm gonna screw it up. So here's our origin, and let's say we have this is 1, 1. To rotate that clockwise, well, this is 1, negative 1, negative 1, negative 1, and negative 1, 1. Okay, one of them gets flipped to the other position, and the other gets negated and flipped. So I think we just send the right to the left of the previous one. So there's that. There's that. There's that. And there's that. And then the other one we negate and send to the other position. So that gets negated. This gets negated. This gets negated. And this gets negated. Cool. So we have at this point to p dot, well, x equals p dot y, and y equals negative p dot x, right? And counterclockwise is just the other thing. And I guess it doesn't really matter if clockwise and counterclockwise are accurate as long as they're inverses. So x becomes negative p dot y becomes p dot x. There we go. Okay, so Val, base shapes. So we're gonna take from the input, and what's our input look like? Oh yeah, I don't really have a clean way to parse this. Often I'll take an iterator of lines and then take while non-empty or something like that. I guess here we can do a loop, or I suppose an unfold. Okay. Yeah, so we're gonna make a list of shapes. List of shape state. Um, or hold on. Iterator dot unfold. So we're gonna have an empty list. List dot empty shape. And then we have our, well, I guess that's what we're making. That's what we're building. So there is still going to be that empty list. Oh, no. We're just unfolding values. Our state is our lines. So we start with input. So we have these lines. And I guess we can match on the head of that, right? So lines.head.match. I don't think we'll get to the point where we're empty because we're going to reach these here eventually. So case. I know there is some index followed by a colon. In that case, then we are actually doing something. And that something is lines.tail.take while non-empty. And this makes a mini grid. So we'll do like a points iterator here. So we want the area around that grid. This is take. And it's always going to be 3. So we'll just do take 3, actually. Yes, I'll take 3. And let's just make this a vector because that needs to be an index sequence for this to work properly. That points iterator. So val grid is that area around the grid, points iterator. And we're gonna map for each point if, or rather we're gonna filter. So we're gonna filter for points such that grid at that point is equal to hash. And from that, we make our shape. So shape is going to be from that to set. Okay. And then our state, well, we're going to output the shape. So val shape equals that. And we output the shape. And our state becomes lines.drop 5. Great. And then in the other case, so a line that doesn't match an index, then we just do none. So that should parse. Let's make this whole thing a list. Dot to list. Okay. And we could draw those out if we those look wrong. Like in particular this one here. looks wrong. I think I did the wrong set of points. So we filter forward grid equals that, right? Let's print the shape. Um, so val points is going to be this. Okay, and then we're going to do area around the grid. Draw. So this is a function from point to character. So if grid at that, or I guess if points contains that character, then we draw that, else we draw that. And we're going to print that. Okay, let's show the shapes we're parsing because I kind of feel like they're backwards. That's odd. You're printing, right? Draw gives us a string. Oh, we have an error here. To list is not a member. Oh, right here. We're just not even compiling in the first place. Okay. So that's our first shape. And oh, we don't even have the correct elements. Here's our second shape. Our grids are only 2 by 3. If we take 3, each of those lines should be 3 length, right? Oh, no, lines that tail that take 3. I see. Yeah, we were parsing the index line in there. Oh, I'm not going to leave you. I probably will still be solving this. um, Alex, are you going with the binary encoding of this? I mean, I could very easily just turn this into a bit set instead of like a set of points. So that's in there. But I don't want to encode it in binary because then like we have to translate it. I guess the shape itself can have a location and a rotation or whatnot. But there's so much indirection that I'll probably write bugs my first approach doing that. It wouldn't work because you also need to keep track of how many times we used each present. Um, well, let's at least parse our other bit. What is this even called? The second section lists the regions. So val regions equals input.collect. And we can just match for those particular cases. So there's an area, and then there's counts. Regions, we're gonna make this two lists. No, we're gonna have them zip together. So we have The state size is huge. Yeah. Yeah, we'll need to reduce in some way. We can't brute force all the way. But like, I don't know. Maybe if we find like local optimal packings, we can at least tile that for the first 50 or so of these, and then go optimize. And you know what? Maybe the problem is easier than we think, because we don't need to find any optimal packings per se. We only need to know if it fits the presence or not. So maybe we can determine that doesn't fit without actually finding an optimal packing. That's there. I don't know how we would do that, but if we could, that'd make the problem a lot easier, wouldn't it? Um, this is the overworld from Mario 2 on the NES, or it was also in SNES in the All Stars. It's a good tune. All right, so let's take the area. You know what? No, we're gonna take X and Y of that. So we're gonna do width and length. Width X. Oh, width, and then there's an X, and then there's a length. So we have an area w.toInt and l.toInt, and that's paired with counts.split on the space and map each of those to int. So this could be a vector of tuples, and they're going to be area and list of int. Looking at the leaderboard, do you think we're overthinking it? Ooh, that's good. That's good news, because brute forcing this is daunting. Oh, people are already done. People are already done. Overthinking indeed. Okay, I believe that. Area dot bounding. No. Area of, I guess, 0 until that. 0 until that. And 0 until that. Okay. There's no way to we could just do, I mean, a stupid thing we could do to reduce our space is just to count the ones where the volume of the presence doesn't even match the volume of the thing. So the volume of the shape is just the count. Yeah, sure. Base shapes, we want this to be a vector too, 2 vector, because we're going to index into these. So regions.count. So case we have an area, and we have a set of requirements. I think I want this to be a vector too, because we're going to index into it. Nah, that's fine. So area, we have counts, and for each of those counts dot, well, let's just map the volume. Counts dot map, or zip with index. So counts dot zip. Oh, we just zip with shapes. Zip with shapes. And we're going to get the volume of that. Well, present volume counts dot ship zip shapes dot map. So case, we have a count, and we have a shape. It's gonna be s dot size. No. S dot points dot size times c. And why don't we do this size in long, just in case. And we're going to count the cases for which area dot size in long is greater than, or is that less than, or let's do it the other way around. So present volume is greater than or equal to, wait, we need to know how many can fit. So less than or equal to area dot size in long. Strip shapes. What do we have? Base shapes. Oh, sure. Base shapes. This gives us at least an upper bound, right? Or a lower bound. Lower bound. Then we can just turn that into filter. And regions dot size. I want to know how many of those there are. We just go from left to right and top to bottom strictly to find the best placements. Yeah, I just feel like that'd be too large. I mean, some of these have a lot in them, right? Oh, I guess by a lot. Hmm. I mean, there are a lot of presents in some of these. And it's 50 by 50. It's like a 50 by 50 area where we're trying to fit roughly, I don't know, 300 shapes, 3 to 400. Present volume, list along. Oh, we need the sum of this. That's 408. Okay, so we have a lower bound of 408. So over half of them are just too much by volume. Ha, that's it. That's it. Okay, continue part 2. And we just get to click. Finish decorating North Pole. Okay. Okay. Thank you. Thank you. Uh, we got the stars. Okay, you really had me worried about that problem, Eric. So, I mean, you can make this harder, given like you can definitely do harder inputs, right? I mean, the only reason, so that is a lower bound. The only reason I wanted to try it is because other people were already done, and I thought, well, maybe they're done because it's easier than we thought. Okay, I barely kept second place in the Scala leaderboard. So this is my first in like 4 years not winning that one. And how are we doing here? Who's all done? We're still waiting for Zuno. And Alex, I'm sure you'll get there in just a minute. And who else is in there? Tarkik, are you on here? Now I think about it. I don't think I've seen Ice Cold Witch in here. I know Icy Black Deep is here. Okay, it turns out it wasn't that bad. I didn't even need all of this. Um, I didn't need most of this. It just counts. Um, Eric, you were intentionally trolling us over there, right? You knew we'd overthink it. 'Cause it definitely can be harder, can't it? If you just give a trickier constraint or a trickier input constraint, you know? Okay. Hmm. Let's see the calendar. It's finally animated now. Obviously trivial or obviously impossible. That's good to know. I feel like that's definitely been a theme this year is know your inputs. Day 11, that definitely mattered. I'm pretty sure that matters a lot in day 10. I just haven't gone to doing that fully by hand yet. I mean, I've done it literally by hand, but that doesn't scale to however many of those there are. I missed a story bit. I'll have to go look back at the Decorate the North Pole again. You get a well-deserved break. Great. The elves will have plenty of time to prepare for Christmas. Great project management from them. That or problems aren't always what they seem at first, which is a good reminder in general. Yeah. Like very often in the real world, the problem you're working on isn't the actual problem you should be solving. True. Yeah, very true. That's been such a theme this year. I've run into it, and then like once I realize what I'm doing, and then go on to like someone else's stream that's still on or something, I see them doing the same thing. Um, so I wanted to do a little retrospective and go back through the calendar at all the problems we solved. And I don't know, we could even call it a tier list. Um, so retro.md. You just want to encourage people to take a step back and think rather than just diving in. That's completely fair. I like that design actually. Hmm. Okay, so let's look back at day one. Secret entrance. Do I even remember what this was? Oh yeah, so the dial rotation. So part one was counting all the times we land on zero, and part two was counting all the times we skipped past zero. And I finally got a closed form I was satisfied with, but definitely uh, the edge cases were getting me there for a while. Um, so here it is. My final version is short, but I think my big mistake when solving this one was not to just have simple test cases, right? Like you could find this a lot easier if you just have simple test cases in line, run your function against that, um, rather than doing kind of guess and check. So I had a lot of hubris going into day one, thinking, "Oh, this is going to be a one-liner. Let's just knock these out." And testing would have saved a lot of time. You've never been able to solve this, even if I wasn't listening to the stream. That's fair. I mean, I wouldn't have been able to solve it if I wasn't listening to the stream. I mean, I guess I would have seen at some point that people were solving it quickly, but who was it that mentioned that? Oh yes, you, Alex, you mentioned it. What do I think of data science? Seems like it'd be fun, but I've never done it myself. I like data viz. And I like messing with numbers, but it's probably no, a lot of mess and a lot of magic and a lot of trying to clean up data properly. So let's look at day two, 2025. Um, Day two, he could solve regular expressions. Although, again, this is one where, yes, regular expressions is a fast way to solve it, but it does feel like cheating. So for part one, what even was this? So we have a bunch of ranges. Um, and what made it invalid? Made only of some sequences of digits. By looking for any ID which is only made of some sequence of digits repeated twice. Oh, right, yes. So you match it and then you repeat it with itself. This wasn't too bad even without the regular expressions. So definitely a fast, easy day. And I don't have too much more to say about that. Oh yes, yeah, brute forcing just works. That's true. Yeah, brute forcing totally just works here. You could diminish your search space a lot if you generate these rather than, check everything. Yeah, like you could very easily create a range that encompassed terabytes or at least gigabytes of information, right? So I guess since today too, we didn't have to optimize that. But that could be the part three if you want to up the ante. All right. Day three. This is a joltage problem. Oh, I think I quite enjoyed this one actually. So what is a total output joltage? So for part one, the sum of the maximum joltage from each bank. Okay, so I think this is a day. Yeah, so for part one, is you just take two of them in order. So you have to get like the largest possible sum from, or digit, or number, I guess, by choosing them from left to right in here, right? And I think this is one where thinking of it recursively made it easy for me because in order to do it recursively, I had to think about well, like what the recursive case actually looks like. So joltage, where am I actually calling it recursively? Oh, I'm not, this implementation is not recursive anymore. So I changed this to a scan left. But the point was I was thinking about like what we needed to have in the next iteration. So in the next iteration, we can still only choose so many of them. So we choose I plus well, you subtract B, and B is like the number of batteries left to collect, right? So we take the first N minus B batteries. So thinking backwards, thinking about your base case helps a lot there. Um, yeah, I enjoyed that one, and I enjoyed writing this nice little bit. Was as like compact as I could get it. Oh, day four. The problem where you had to apply operators to numbers listed in columns was hard to parse. Oh, yeah, transpose and Scala really helped there. I think the problem statement was hard to parse. I misunderstood the problem for a while, and I don't think I ever actually cleaned it up. But we'll get there. So day four, printing department. Okay. Oh, wait, no. Day four, 2025. Oh, I don't know I have it here. 25 worksheet. Now, did I run into some trouble with this? I don't think I did. Um, okay, so for answer one, we just got all the accessible roles and counted them. And then for part two, we would repeatedly get all the accessible roles, but then we'd remove them. So find the accessible roles and diff. I think this is another case where taking a set of points maybe makes that easier, because then I could just diff those out. And I guess having this library method helps. I already had this built in, so I can just take the surrounding and count how many of them have a fewer than 4 surrounding. Okay, cafeteria, the forklifts, breakthrough. Oh, and then spoiled ranges. So I think this was a day where we could just kind of write what it was. Yeah, so fresh intervals. Ah, the trick here this day for me was not to use the built-in range type. Like the built-in range type can include longs, but the methods on there like dot min or dot max all return int. So you can actually get overflows in there, which is quite annoying. But my type doesn't do that. And yeah, this was another one where it's just a one-liner in like library code. So we count the IDs for which there is a fresh range that contains ID. Yeah, and I think part two was almost easier than part one, right? 6. All right. Um, my code here is still a little messy. And that's because I misunderstood for the longest time. I thought we were just kind of left aligning these. And so I just took all my numbers and I started left aligning them. But it turns out the white space matters from the very beginning. So when you parse it and you split on the spaces, then you get yourself into a little bit of trouble. So yeah, just starting with the transpose would have done the trick, and like just transpose the input text altogether would have made it a little bit easier. And then you parse the digits there. I had the thought that on this problem, if you transpose a text, you could just like slap parens on it and throw it into Lisp eval, because then this is in like is this prefix form of the function? Yeah, I kind of basically started over. Well, not completely. I didn't completely start over. I should have started over because then I wouldn't have had to write this weird state machine. But yeah, that's one I'll go back and clean up still. um, laboratories. Oh, okay. This is the first day where I choked. Um, I think I basically solved part two first. So what I was building was a count of how many lasers ended up at each step. And in order to calculate part one, I was just like, well, if there are so many beams at the end, then subtract one, and that's the number of splits. But if multiple beams at once are split here, that still just counts as one split. So what we wanted was a number of splits that were hit at all. So it took me a while to realize I was misreading the problem. And I think it took me a while to choose to optimize it properly. I think in my head I was like, this won't need optimization. I I know I miscounted. But yeah, you optimize this by making, or I did. I optimized it by making a map. But I guess you could do that with just a vector and update at that index instead. But this right here is the meat of it. And then I just tacked on a part one or solution by like messing with my part two data structure. So beam states is a map of int to long, like how many beams showed up at an index. You did something wrong at first. Sorcerer heard Lisp. You did something wrong at first and then spent a lot of time thinking there was some hidden definition of what split meant. Ah. You also overthought this one and calculated a number of ways. Yeah. Yeah. This was my first like reading comprehension issue day. Um, Day 8 though was a worse reading comprehension issue. Oh boy. So the junction problem, uh, the networks. Um, okay, my code's longer than I remember for here. But what am I building? So components is, oh yeah, I'm building a list of components. This still isn't all that well optimized. I think when I was doing this on stream, I had to run it in a separate sheet, but all I had to do was make this a lazy list. So there's a lazy list in here somewhere. Here, all the states, a lazy list. I hadn't had that as lazy, so I'm still computing all the components for everything in the map. Yeah, I was able to do this without union find. And the tough part in my code anyway is that for part one, I basically just built up an adjacency graph, right? So my states is a list of adjacency graphs or a lazy list of adjacency graphs. But you kind of need to do part two efficiently. You kind of need to track the components as you're growing them, not just the adjacency graph. And I didn't want to redo how I was doing my search, my connect. So I basically took every adjacency graph and then calculated the components of that graph. But that wasn't too bad. Like calculating an individual opponent, you just get you just like keep flat mapping the adjacent flood fill that, right? And this you just iterate through, keep getting points that aren't already in the component. So index where fully connected, I still calculate a component. Uh, yeah, I just get like the first key and I can calculate its component and calculate its size. But if I already had components, then I could already know if there was a component that encompassed everything, because I'd already have component sizes. You started day 8 as your start point. You totally forgot how to code even the basics. Fair. You kind of implemented a DSU by starting over because of part 2 in this one, a disjoint set union. Yeah, that's fair. Yeah, if I were to do this with some sort of union find, I think I'd normalize each set of components to I guess just whichever one we connected to first. Um, but if you're doing union find, you kind of have to do it with a mutation. I guess you could do it functional, but it's not going to have the same efficiency because part of it is just like you can just change the parent of a node. Brett, you did union find? Yeah, that's fair. I could come back to this and optimize part two with the union find. But yeah, this is the problem where this wording got me. If boxes are already in the same circuit, nothing happens. And just reading everything else above that, I thought they didn't want to connect anything if they're already in the same circuit. So I thought they're trying to save on extension cables. And it took me way too long to realize that 1,000 connections will connect the whole circuit if they're always between distinct circuits. And I think that's partially because I didn't look at the input and realize that there are only 1,000. I had to have it like fail before I was seeing that happen. Yeah, and once that happened, I think getting part two felt straightforward. Yes, yes, I think you had that bug. Someone else mentioned having that issue. Was it Narf? I can't remember. But yeah, now day 9. Oh yes, day 9. I have drawings for day 9. I have an article for day 9, by the way. I posted it earlier, but for people that are just now showing up, I'll post again. So drawings for day 9. Uh, yeah. So with this one, I wanted to do some sort of like range compression and do like a flood fill-ish thing. But I was struggling with the edge cases, right? And then I realized maybe this kind of heuristic works. If there's nothing crossing a line, then it's all one color. It turns out with the input we had, we didn't have to run into like an edge case where I don't know, where like a line goes in and stays next to itself. And since the line is green, even though it crosses the boundary, the interior is still all green. But yeah, it turned out that for day 9, this code ended up being really short. Yeah. And the meat of it is here. Just to check that there's no intersection between the lines and the current rectangle that you're testing. Coordinate compression was fun though. Yeah. um, yeah, I think if I were to try again with coordinate compression, I'd do it in a little bit of a different way. And what I would do with these boundaries, I would compress this line here to one coordinate, and then I'd compress everything else here into another coordinate. So there would be some coordinates I'm not compressing that much at all, but then I can just have squares that match the same shape and do flood fill there, and then we translate between the compressed squares to the full ranges. But I didn't think about doing it that way. I kind of thought instead about building more of a disjoint set of areas, right? I wanted to break this down into boxes. And that was too hairy. And I was running into too many edge cases while working on that. And it turned out like this is just something that's fast to write, and you don't happen to have the edge cases that make it fail. Your algorithm for looks for lines crossing what? The boundaries of the rectangles. So you take 2 red tiles, right? And then you build a rectangle there, and you just look for lines crossing that boundary. And I just define my lines as areas themselves, and my area has an intersect function, right? And my area is defined in terms of like an X range and a Y range. And check if to find the intersection of two areas, I just find an intersection of the X intervals and the Y intervals, and return a new area with those intersection intervals. So it's just like intersect all the way down. Intersection between like the intervals itself is pretty simple. Well, if the object is a large L shape, um, well, I don't have to worry about that because they are just lines, right? Um, what do you mean? So like the rectangles themselves that we're testing are just going to be rectangular, and the lines are all just 1 by n rectangles. So I don't think we have to worry about L shapes. Um, yeah. So let's look at this. Was fast once I had my light bulb moment, but it took me a while to get my light bulb moment. And part one was just a quick, easy brute force. The rectangle isn't colored. Oh, yes. In this case, the rectangle isn't colored. But as it happens, our input looks like this. So an uncolored rectangle is never going to be as large as a rectangle that's inside this big circle, right? So yeah, the largest one happens to be it. Otherwise, I would have had to do like, I could have done a test a single point and see if it's green, and I can do that by like counting even odd. So if you cross an odd number boundaries, you're green. I did use something about the input. And in fact, I used two things about the input because, again, if this is a rectangle and one of the boundary lines looks like this or something like that, my code would reject this because that boundary is being crossed, even though all these tiles are green, right? And it's only out here where it's yellow, but a yellow can't get into this pocket. So yeah, definitely I was taking advantage of the input shape there, but it made for short code. Um, yeah, I think I was trying to get someone else to look at the input shape here. It does help. Yours is agnostic, yeah. I think if you did range compression, yours would be agnostic. Day 10, the factory. So I think for part one, a lot of us recognize it as just an XOR. And those answers started flowing in a few minutes. So I still haven't done this properly. I think it is important, no matter what you're doing, to recognize that this is a system of equations. And I think I can solve it just with a series of substitutions, and then do like a tiny brute force on like the final range or something. Like I can really constrain things if I mess around with equations. And I've been doing a lot of these by hand. So there's some here. I have some in like some other worksheets. I didn't want to write Gaussian elimination. And so earlier today, just before midnight, I imported a constraint solver, and I did it that way. Um, for this one, I don't think it's A star. I mean, I tried with Dijkstra. I think I did do an A star. I'm not sure my heuristic was all that great. You insta constraint solved it. I still want to go back through because Eric says you can do it with for loops in high school algebra. You don't even need linear algebra and Gaussian elimination. let alone, constraint solvers. Oh, could I talk more about the system of equations? Um, yeah, so each line is a system of equations. So we could draw out one of these real quick. Um, where shall we do this? In fact, you know what? Let's solve one of them. Okay. So in this case, the first line, let's use that. And we need 3, 5, 4, 7. So I'm going to label these buttons, I don't know, A, B, C, D, E, F. So some number of button presses equals 3, right? And that's the sum of all the buttons that have a 0 in their index. So that's A, B, C, D, that's E and F. E plus F equals 3. And then for the second one, everything with a 1 in the index, so that's B plus F. B plus F equals 5. And then everything with a 2. So that's C plus D plus E. C plus D plus E equals 4. And then we have 0 plus A, B, D. A plus, sorry, what? A plus, one sec, plus B plus D. And this is 7. Yeah, Eric, what was saying is true. Technically, the high school algebra approach is probably identical to other linear algebra approaches, but your solver literally plays solve for x over and over until it wins. Yeah, I believe it. So, like, what I'm planning to do is just model the equation and just do substitutions. So I'm not going to do like the model it as a vector and like add rows together. And I think that works. Like, I don't know, the handful of them I've solved by hand. It seems like you could do it that way. Should we solve this one? Um, we could. We don't need to subject ourselves to that, right? Um, but like we want the full sum to be minimized. If we add these two rows together, A, B, C, D, E, and then D, then I guess we have 2D. So this is going to equal sum. There's a minus D, and there's no F. Minus D plus F. Right? So if we translate that over, then it's like adding these two. So 11. So the sum is going to be 11 minus D plus F. I think there are multiple ways to get here. But in this one, we could say like maximize these two. And in that case, maximizing the sum D plus F where, well, we know F is at most 3, or F is at most 3, B is at least 2, D is at most 7. So that sum is at most 10. Uh, hmm, I don't know. That's not fully solved, but we can move on. So E plus F, you search the different variations of E plus F equals 3, which affects other equations as well. Yeah, I didn't go down that road. This one's not shaking out for me as quickly as I thought it would. C, D, E, F, B. Oh, I guess if we added these two rows, then we have just A on the other side. But what you could also do is like you solve for one variable, or you solve all of them in terms of one variable, and then the sum can be expressed in terms of one variable. And then at that point, you just minimize or maximize that variable depending on what does the sum. And at that point, there's not like as much to brute force because you're only looking at one or two ranges instead of 6 different ranges, right? And some of them just shake out completely to um, complete solutions. So it seems like at least 2/3 of them you can just solve completely. Um, but yeah, this one I will definitely revisit. And if I get it, I'll share that sometime on a stream. Um, yeah, I think most people here either. I saw, who was it? Who's the Erlang programmer? I watched him do it with a Gaussian elimination that I think he implemented himself, and then did like a search over the remaining. And I think other people use solvers, so I got this solver as a recommendation from other people in the Scala Discord. Your solver spends 750 milliseconds in total. Actual hint, skip if you don't want. The sum will be expressed by however many free variables you have. So you can constrain that further by looking at what values each variable are even sane. Okay, yeah. So I think I've, so you might have one or two, maybe 3 free variables, and then that's like a much smaller space to search through, especially if you add constraints that you found. That doesn't feel too spoilery. Um, yeah, I'll definitely try something like that. Eric's been trolling us this year. Okay, day 11. Day 11 ended up being pretty easy for me. What was part 1? So just count paths from one to the other. And this was, for me, this was just a recursive count. And I don't think I even used tail recursion. So if we hit the goal, then that's 1. And if we hit anything else, that's a 0. So we sum every path that we find. We just search from our current location towards the goal and keep searching through the adjacency map for the current location. And then this works for part 2 if you just memorize it. And I suppose the other insight was doing this in parts. Like do that in parts and then multiply them together, rather than actually computing the paths all the way to out and doing some sort of constraint on that. Because the number of paths between this and DAC are just, that maybe like the 10 different paths you could take to here. And for each of those 10 different paths, the 10 different paths you can take to here makes 100. He did memoization. I don't know if you all saw visuals for this. I didn't make a graph viz, but Advent Day 10 visualization. Oh, we should search an add in the code. I think it's worth looking if you haven't seen one yet. So day 10 visualization. And here. So there were all these choke points that made memoization really good because you're basically searching from one of these choke points to another choke point. And once you have the optimal path between a couple different choke points, then there's no need to like search again when you're searching to the left and right of that, right? And then memoization just kind of gets you those choke points in there by default. They're probably the most used, the most looked up things in the memo because that is always like an intermediate goal. You failed in the memoization. Did you have a bug in your memo? Yeah, I did the same thing. um, and looking at the puzzle input, I think there's kind of a hint here because you scroll through this and some of these lines are really long. And then you look at something like GMK and you realize GMK appears 14 times. So it has a high out degree. It also has an high in degree. So, so if you didn't just guess memo and see that work, I guess you could look at your nodes and count their degrees and be like, hey, there's some outliers here that really form choke points. And then you could do some sort of optimization based on that. I think you'd probably do optimizations that aren't memo that still take advantage of those choke points. Right? If U to out, yeah, you can basically count, like, if you can do U to out without memo, then you could also just do every choke point to every other choke point without memo. And then there aren't that many paths to calculate. So it'd be like, I don't know, 4 by 4 by 4. It might be like 1,000 times actually longer than part one, but still. Okay. I guess for the DAC and FFT, you could find the shortest path between meta nodes that contain that, and then you use a choke point that's I'm not sure. Still, just using memo there helps a lot. But definitely a fun problem. Um, Day 10, I'll get there, but that one's fun too. Um, they've all been fun this year. Thanks a lot, Eric. And Christmas Tree Farm, we just did this. A simple check on the lower bounds does it. I really thought I was going to be here all night with that one. All right. So, where we go from here, I do want to keep Advent Code going for the rest of the month, sort of. Did you finish the parsing problem I was working on yesterday? Oh, yeah, day 19. I could do that. So the parsing problem, I had thoughts about that one. So day 19 from 2015. Um, I think I do actually need to parse it more. I tried all sorts of searches through, and that wasn't working. I think I need to actually use the shape of the input. So where is events? And we have 2015, day 19. Right. So there are all these replacements. And let's look at our actual puzzle input replacements. And I think we need to actually analyze what's going on in these replacements. Like the one big obvious thing I noticed right away is that argon doesn't expand into anything. So doing those argon counts might be interesting. This FYF, there is an F, there's no Y, but I don't know, like maybe if we just counted instead of like trying, like say TI, we know that that can expand into any number. So like if there are 5 TIs here, then we don't actually have to like add that as part of our search. We just know that it included so and so many steps, right? And we're always getting longer. But the question is like if we can figure out how much we're getting longer by on each step, and you keep calling a parsing problem. Like maybe I should just run this as a parser and try to parse this thing in terms of this set of replacements. Your default was a CKY algorithm, but with counting. Makes sense. And same thing with calcium. It can grow or do one of these things. It can do one of these things that end with argon. And perhaps a good first step here, perhaps a good first step is actually just parsing out the elements. And in the end, I'd like to know how many elements we have, and that'd be like an upper bound for the number of steps. Kaka is a hint, you think? Well, I mean, there's also uh, Tai Tai. Um, my brain is sitting here thinking Kaka and Titty. Just some like toilet humor. Like Titty Kaka? Yeah, totally. That's exactly what I was thinking about. Um, and then silicone turning into calcium silicone, and the calcium can just expand on itself over and over again. So like counting, I think I should count the number of argons for sure. This Y doesn't expand. I should count the number of Ys, and I should look for any element in the right side that doesn't appear in the left side, because there probably are more. Rn, does Rn appear? Okay, Rn. Yeah. So I think to solve this, we actually have to look. We have to look at the input. Day 19, worksheet 2015. Okay. It's possible that we abandoned search altogether. I'm just gonna do try 2 on this. And we're still gonna parse out our replacements. But now we want to take a string and just get all the elements. So def elements from a string is just going to be, let's make that a list of string. And we could just count the capital letters basically. Or here, a better idea, if we take S and we zip that with s.tail. So that's a sliding window of 2 characters. Or what am I doing? We have a sliding window function. So s.sliding, sliding 2. And we filter the ones that start with a capital. Actually, you know what? I want to mess with the individual characters. So I think I actually will zip with tail s dot tail. So we want to filter on that. So we have two characters where A is upper, and then if B is lower, actually, let's do this. Let's do a collect. So we'll only consider cases where A dot is upper. A is a character, right? Why isn't any? I think it's just my compiler being a little bit behind. So if A dot is upper, then if B dot is lower, then we make a string from AB. AB, else it's just A. A dot to string. And those are our elements. We still have one more element at the end. So about end, it's going to be, if the last character is capital, then we add that on. So if s dot last dot is upper, or we'll make that an option. Option dot when it's upper, then we just do s dot last dot to string. Okay, that gets me the elements. So about ease, just call them ease plus and dot to list, I guess. Oh, I guess ease needs to be a list. Let's do it that way. Prepend it to the list. Okay. So if we get elements from this string, for example, I'll catch up with chat in just a sec. Great. He reduced a medicine formula to E. Don't know about building it though. Yeah, I do still kind of want to reduce. And that in a way is kind of sort of like parsing this. We could sort of take a look at it and try doing it by hand. But the thing is, I know that reductions aren't unique. I mean, the reduction probably is unique, but you can fail and have to backtrack. And there are a lot of different ways to fail. So you can't simply do replacements backwards. So I think I have to do something smarter. Okay. Now let's just get all our elements. Val all elements equals replacements. Flat map. So case we have something on the left, and then we have several on the right side. So we're gonna get elements from R, and then we can just cons L onto that. Yeah, and then we're just gonna do dot distinct at the end, and that's all elements. All elements. For each print line. Okay, let's see what those are. And I want to know which ones don't repeat. So we're going to do all elements dot toSet dot diff all the keys. So replacements dot keys key set, I think. Oh, I guess we just take the left of that. Replacements dot map, take the left side dot toSet. Okay. This shouldn't be stalling. Okay. Y, AR, RM, and C. Okay. Wait, C is an element? Oh, right here. But it always appears. Does it always appear with R? Should we just call CR the element? We could call CRN the element. Now, does RN always have C in front of it? No, there's an ORN. Okay, so we have C, RN, Y, and argon. Isn't there an advent of VHDL from Jane Street? Yeah. Someone's posted a link at some port, FPGA. And I think it's basically choose a problem from this year and implement it in FPGA. So I still have to choose one. But so before I finish this problem, um, here's my plan for this year. So I'll be on tomorrow, and I think I will start Cinecore. And then I think I'll just continue that on weekdays at the normal admin code time until it's finished, however long that takes. And then from there, maybe FPGA, and then maybe if there's a lot of time, finish out 2015 or something like that. Um, and I'll be a little bit more relaxed in my schedule. So I think on weekends when I'm doing things, I might show up late or not at all. But on weekdays, I'll still show up around the advent code time and do some sort of problem. Mostly Cinecore. Do I do FPGA stuff? No, I have used a hardware description language once. Are you familiar with the with NAND to Tetris? NAND to Tetris, really fun project. You basically start with NAND gates and you build all the way. Well, you build the circuits. You build a CPU, an assembler for an assembly language to machine code, a VM that runs on that assembly language. Um, and then you write a compiler for the language that runs in that VM, and from there, you can then implement Tetris. Um, and you can do this like at every step along the way. It's like a simplified version of like what a computer is actually going to be. So you can just build a whole computer that you understand fully yourself, um, and then it it feels very cool to understand the whole thing. So that's the part where I use like a hardware definition language. And I had a hardware class in college, but I don't know that we actually used I don't know. We used um, Logisim, like a circuit simulator. Um, and I think I built a CPU or at least an ALU in that, but it wasn't the same as this. And this book, I highly recommend Elements of Computing Systems. You did Verilog in college? Yeah, I haven't used Verilog, but interested in using this hard camel that they have for that FPGA thing. But that's the plan. Cinecore tomorrow night, and then throughout the week until we finish. You don't fully understand flip-flops. Maybe it's time. Yeah, build some in Minecraft. I taught my younger brother, who I think was in middle school at the time. I taught him how to build circuits in Minecraft, and I gave him like progressively harder challenges until I got him to build like a full adder, like a binary adder. And I just had him do it in Minecraft, and that was pretty cool. Mhm. Infinite loops to hold a bit. That's a good description. Yeah, it's a loop circuit with a stable state. But just get like Logisim or something and draw out some circuits. I'll introduce that kid to Factor. We have played Factoria together. He started playing last year, and it was really bad for me. The Space Age came out, so we started playing Factorio Space Age. It's not good. It's not. You stop sleeping. You stop talking to friends. You stop showing up to work on time. But it's a lot of fun. I enjoy Factorio. Um, there's a game I want to play, and possibly on. Oh, hey Jeff Irwin, how are you? How'd your admin of code go? Introduce every kid to Factorio. Yes, yes, totally. Introduce every kid to Factorio. Um, are you familiar with any of the games by uh crap? So there's a game called Shenzhen IO, and this one is basically you are building things in assembly. So I'll find some screenshots or something. It's a Zachtronics game. Zachtronics has all kinds of games like this that are like low-level computer stuff. And this game comes with a manual, so you can print out like this 100-page manual of schemas for all this hardware and like documentation for all the pieces that you're using and wiring together. So you wire these together, you write some assembly, and then you build little hardware things. You love Exapunks? Yes, I'll enjoy that. I think I'd like to play that on stream. That seems really fun. Um, yeah, good sidetrack. Try what is that? KOHC. Shenzhen is a solitaire card game. So is Balatro. Balatro is another game to avoid. Or Balatro. I think that's how you're supposed to pronounce it. But Balatro has a better ring to it to me. Every electronics game is a solitaire game with a programming puzzle minigame. Fair enough. But yeah, any automation game is like addictive. It's acrylic for constructor. You make a CPU by drawing PNP traces. Okay, let me try and copy paste. I might have to look that up, and oh, I might have to play it. Engineer the people. Interesting. Oh wait, it is another Zectronics game. Cool. He plays an engineer working in a semiconductor factory, designing circuits based on specifications. Cool. Yeah, Zectronics games for sure. I'm into them. The food court game from their so there's a mini game inside of their last game. Um, I think we're making some headway here. So we found the four elements that are terminal. We'll call them terminal elements. And we could do the counts of them. So let's take the medicine. Medicine dot elements. or just elements of medicine. And then let's get the size of that. And val, what do we call this? Terminal elements. It's going to be a set of those for C, Rn, Y, and AR. Oh, we haven't parsed out the medicine. Medicine's just the last line, right? Val medicine equals input dot last. Okay, so we have an upper bound of 295. Because every step always generates more elements. And the output has 295 elements. 20th century food cart. From last call BBS. 20th century. Court. Oh, it's also named after a song. Programming and optimizing a food factory. All right. I'm gonna have to go through all of these. Okay, so 295 elements. I want to count terminal elements. Elements dot elements medicine dot count terminal elements. I'm just gonna rename this to terminal. L so we're gonna count terminal. There are 76 terminal elements. Okay. Um, 76 out of 295. And geez, what do we do with that? We could try a small bit of this and try parsing. Well, okay, let's look at some of these terminal elements actually and see how they appear. So it's notable that Y always seems to be surrounded by Fs. So, well, okay, in this case, there's a magnesium afterwards, and in this case, there's one before. But still, what does that tell us? If a Y appears, well, in this case, 2Y appears. So if this step ever happens, then that means that step generated 2Ys, which would mean like there could be fewer Ys than steps to like generate that. So yeah. But it's always surrounded by Fs. And what happens to Fs? They either add calcium in front or add magnesium on the end. Okay, so if you generate these 2Ys, you could like keep expanding that. And then the other thing they can do is silicon aluminum. Silicon aluminum. Silicon can build calcium on the left. Aluminum can do one of these two things. One of which is straight up two of our terminals. So Rn, F, AR. There's with that F again. So I wonder if every terminal step involves an F somehow. So aluminum aluminum can turn into that with the two terminals, or it can add, oh, there's still an F. Um, R, is an RN always followed by an AR? Aha. Okay, so that feels important. If an RN is always followed by an AR, then we can chunk this into bits of RN through AR. So here's one. And why don't we manually decompose this one? So okay, so an RN is always followed by an AR. Now, I imagine you could still spawn more RNs and ARs in between that. So you could get two ARs in a row without an R in between them. And there's a bunch of calciums before a silicone. So that's probably following this rule here, right? So the calciums delete. And there's no other way the calcium can appear in there, right? Because these could only have come from the right because they can't come from the RN. 1, 2, 3. So the number of calciums is the number, is part of the number of steps. So to get here, we do 1, 2, 3 expansions of silicone. So there's 3 steps to get down there. And then silicone, oh wait, there's another RN here. Oh, hold up. We have a smaller problem here. So there's that, and it's part of a bigger problem. So let's just do this whole CRN. We need to skip past that RN to the second AR that we see. Okay, so this is the first bit. And these kind of feel like parentheses of some sort. So inside of that is this. So we can get the count for this. We can do that later. So there's BP, titanium, magnesium. And how do we get those? How do you get B on the left, rather? There are 3 ways to get B on the left. Let's take this, actually. Let's do placements, filter, 2 that starts with B. And then we'll do like a dot for each. Dot for each. Oh my god. Line. Oh no, I closed it. My fingers are not cooperating. Sorry about that. um, but yeah, to get a B, it can come from a B. Oh, right. So we're just building calcium on the right. That's not what we're looking for. To end up with B on the left, that can happen from magnesium. And it can happen from titanium. So maybe a previous step was either magnesium or titanium. And there's a P to its right. So we probably want this one, right? So BP, and that's titanium. And then the 2 titaniums can shrink into 1 titanium. And then the magnesium Where did that come from? Magnesium can spawn the titanium to its left. Okay, so this is probably the root here. Oh wait, that appears there again. How many RNs are in here actually? RN. So the actual end argon appears much later. So argon, argon, it appears here. So the full string then is this. Oh, nope, there's another R. Is the end argon all the way out here actually? It seems like the end argon is all the way out here. Because this whole bit yeah, this whole bit here is kind of immediately followed by another thing. So I think we just look at chains of Rn through argon. By the way, if anyone knows what element Rn is, please let me know. And these are all preceded by silicon, or are they followed by silicon? Argon's always the end. So how do we get silicon for an Rn? SiRn. Okay. So that means one of these elements were there beforehand. So we look at the lead element. And in this case, it's a silicone. So I'm going to prepend silicone to that. And silicone, Rn, magnesium, argon goes down to Ca. Nice. So this is, how many steps is this? The BP came from titanium, right? So this is one step, 1, 2, 3, 4, 5. So this drops to silicon Rn through the argon, the calcium after 5 steps. And then the calciums you just count. They each appear one at a time, right? That's probably this calcium just expanding itself. Rn is radon. It's silicon, not silicone. Fair? Silicon. Great. So now we would reduce this bit here, right? No, this nests. Okay, but basically we look for things that lead up before Rn. What happens before Rn? Thorium, titanium. Is that phosphorus? Carbon. But basically there's going to be some sort of XRN. And I worry that some of these might be able to expand. Well, I mean, they can expand, right? So say O. O could have expanded to a bunch of other things. So I think, I don't know, you kind of have to look for a case where the radon is preceded by a lot of things. I suppose we just take argon, right? We take argon, and then we take everything until the next until the next radon? And do we assume that came from whatever made the radon? I think it might be fair to do that. Yeah. I think we at least have enough to make a parse function. Decaying uranium makes radon. Fair enough. Wait, do we have uranium here? What is the symbol for uranium? It's just U, right? Yeah, it's U. There's no U in here. It's too bad. I guess we get a lot of radon from oxygen. So def steps to get a list of elements. Let's spell that out. So there's some sort of recursion here, and I'm gonna start. Let's start with steps that have radon and argon. We'll just make an assertion here. So whatever this step function is, we might rename it later. It's going to assume that we're ending on radon. Let's start elements dot last equals argon, rather, not radon. And we'll assume it contains some radon. So we find the index of the radon, and then we take everything that's on the inside and we reduce that to any one of these things that can fill that gap. So we search for those. I guess we could make a list of those. We could call them our goals. So replacements dot map. So we get the right hand side of these. I have a sense that I'm overcomplicating these. Well, in either case, I do think that we want to reduce everything to the left of the radon to just one element. I don't know. I'm not completely sure about that. What I'd like to see is this. I want to see the whole nested structure of this. So I could start this top down. Actually, you know what? If this is the first radon and the matching argon is here at the very end, how does this calcium and fluoride show up? I suppose, right, we could have had an H that expands into something before it expands into something that takes argon. Okay, I think we do need to do some sort of like a parentheses here. So we track everything that's before it. Then we go down a level. We grab everything until we have one radon, and then we find the matching argon. Another hint: think greedily. Um, yeah, I'm afraid to do greedy just because. Yeah, I could just parse this. I could just parse it down. Um, I kind of did greedy when I was doing my search, right? And I kept running into things that wouldn't reduce. There were like far too many things that wouldn't reduce. So I feel like if you start doing this in the wrong way, but maybe it's sufficient as long as you have this sort of structure of the radon through argon. But certainly there's some amount of recursion. Um, and I wonder, given an arbitrary radon and argon, can you always just, well, in this case here, um, I don't think I would have known. Let's see. Yeah, in this case here, I don't think I would have known that I was going to magnesium unless I saw that the silicon was in front. Right. Are there other? I guess they always have. Yeah, there are a few internal goals between radon and argon, and they are distinct between the different groups of like prefixes. I can reduce it because of calcium or titanium. Yeah, and you know what? I had special cased. I had special cased titanium. I don't think I had noticed calcium in there. So there's a, yeah. So I missed this. I mean, I could uncomment that and try it, but I think it's really important to take the structure into account, the structure of the actual input, which has this nested stuff going on. So this is just it is just a parsing problem where you're counting the number of steps, right? Um, well, we have a list of elements ending with argon. We can get the internal stuff. So drop until radon, get the internal stuff, and reduce that. Counting the number of steps to reduce that to one element. No, it's not necessarily one element. There might be multiple. Uh, so no, we can't do it recursively that way. Um, okay, when you say think greedy, maybe it just does suffice to take a single element that's before radon. So the way we're going to do this then, um, at least to start, so elements 1 should be radon. Yeah, elements 1 should be radon. And then we could just try to parse that. So what would that look like here? So in this case, I kind of went from inside to outside, but we take silicon, radon, and then we try to parse what comes after silicon or radon. I guess we try to parse any one of these things that follow a silicon radon sequence. So SIRM. So we find out these replacements. And then we try to parse the next thing as an F. And if it doesn't parse as an F, we look for transformations that give us an F. So in this case, we look at B. Well, no, that doesn't work. Here earlier, we took the BP, we turned it into titanium. We shrunk the titanium. Right, you can't just get a B, but wait, we have BP. Did I do this right? Because there's a PB, no, BP. I guess we just grab elements until we have something that can reduce. Yeah. And then we repeatedly grab elements until we have something that can reduce. But that silicon RN. So if our goal is FYF or MG or F, we see if we can reduce it to one of those. By taking greedily until we hit one of those goals and then we count. So we could have like a reduce to, and then we have goals set of a string. And we have a count. And I'm not gonna bother ignoring search for minimum. I think I have the gut feeling that with this problem, we don't necessarily need the minimum. As soon as we find something, that's probably going to be it. Right? The problem asks for minimum, but that might be just Eric messing with us again. So we have elements. And we get this goals by looking inside. I'm not completely convinced I want to do that. Like maybe I should just straight up go greedy from this. Look for the first thing that can match. Well, no. See, if we start with the silicon, and we do have to do it after the radon. And then we look for the first thing that can match after the radon. And in this case, we're not going to find the string B, but we might find BP. So we find BP, and we're like, oh, we can reduce that. And then that counts as a step. Your other Advent of Code cover band. Okay, I think this is a good start. I don't know if I'm going to knock this out right away. I've got that sleep dip brain fog going on. But let's try. So elements is a list a string And then I guess we could do for elements dot indices, and we'll use this as a size. So n from elements dot indices, we're gonna take n from the elements dot take n, and then we match the right hand sides of replacements. So we need replacements in terms of elements. We're gonna call them rules. So valid rules equals replacements dot map. We're just gonna map values. View dot map values. So it's currently a string. We're gonna do elements on it. Elements to map. Okay, that's a little bit more useful in that form. So we take the first n, and then we look for a rule that matches. So rules dot. Oh, you know what? I think we also want this to be reversed. Yeah, so I'm just gonna map it this way actually. So case K and V, we want the left-hand side as the to be the string of elements. So elements V, so that will be the key. 2K, and that should be our map. So we do rules.get, we try to find the first n. And we keep trying that with progressively more and more elements. I'm gonna drop 1 here because we don't care about 0. Not fold left. And this could be some number of replacements. I don't think the goals that we're searching for even matter here. I'm just gonna assume that we can find something unique. And this reduction is actually just going to be 1 reduction. I don't think we could repeatedly reduce it. Sure, let's repeatedly reduce it. So there's 1 reduction, def reduce. And that takes a list of these. We're just going to move most of our code here. So there's an option of list a string is what we can return. So if it doesn't work with 1 n, we try it again with the other n. So there's a previous attempt, and there's n, and we do prev.or else. We do rules.get elements.take n. And I guess this is an option of string because we're going to reduce this down to 1 element. Well, no. Option of list a string because we still want the remainder elements. So if we do find a reduction for the first n, we still want the rest of them. So that gets consed onto or dot map. Let's map it. Dot map. So this is a single element, and that gets const onto elements.dropN. Okay, so that reduces, and that is always going to be a single step, and we could do that repeatedly until we only have one. Reduce all, the reduce all, and this will return an int. I don't think we need those goals. We're just going to assume they're like unique for now until we see somewhere where that goes wrong. And yeah, we will repeatedly reduce. We could do this as an unfold, a state machine. We could do this as a loop. Yeah, let's do a recursive loop. So we have some elements that we're still reducing. And it's not necessarily going to be just a single character. So we do still want the count. But we also want the end result list a string. And yeah, let's get the count here too. So list a string and int is what we return. And we reduce. Well, okay, we check on as if the length is, well, no, we try to reduce it. And if we can't, then we just return. So we can match on this. So if we are able to reduce it, then we loop again with that as, and we increment the count, or with that new value. And we increment the count, so count +1. And if there's nothing, we just return as and that count. Okay. So now we loop starting from all our elements and a count of 0. Alrighty. So here in our broader steps function, now we found radon through argon in like a previous step before going here. We can do elements dot drop to dot take. We're gonna take well, we're taking a slice. So elements dot slice from 2 until length -1. Elements dot length -1. And we're gonna reduce that, reduce all. And the result of that is going to be a reduction and a count. Yeah, and I guess we do still care about how we got rid of that radon and argon. At this point, we want to hope that the reduction can actually reduce. And then we add 1 to the count. Oh, Gnarf. Hello? Yeah, I can't help but shake the feeling, or I can't shake the feeling that I'm not doing this in a nice way. Like maybe I should just straight up use a parser combinator and plug these in as rules into a parser combinator. And as we're parsing, every time we apply a single rule, we just do a count. Like we've done parsers before. We should just do it that way. And then like we keep track of the state. Um, yeah, and like we kind of use a recursive descent. We should be doing some sort of recursive descent. So we have a parser. It has a state, which is the number of steps. And then, oh, hello there. Rat hole with the braid of 10 people. Welcome, welcome. Um, for me, it is, I mean, it's technically morning. It's 2:30 in the morning. It is a late night. I'm tired. I'm realizing that I think I've realized the structure of 2015 day 19. And I started parsing it, and I'm kind of parsing it bottom up, and this is dumb. And I'm just realizing that I'm on a maybe I can reuse some of this code, but I should be doing recursive descent and going down into this instead, just like a normal parser. And since like a state, like a mutable parser with a state, included in the state, I can track the number of reductions that we're committing and then do our backtracking and whatnot. So I think maybe that's what we'll do is when I'm fresh, I'll come here and I'll just write a proper parser like the JSON parser that we did the other day. Um, and we'll do this nice. We'll do this the nice way. It feels like a shame to delete this code though. Your hard cutoff was 2 a.m. Airport answer the other day? I'd be curious to hear about it. um, yeah, I can save it in another file. I could just comment it out. And you know what? Probably I will reuse some of it. Probably I will reuse some of it. But let's see, just for reference, let's go to an actual parser. So day 12, 2015 is a parser. And I have the things that I'm trying to parse. So I guess the things are going to be whatever's on the right. And depending on the thing I'm trying to parse, I have some different rules. So if I'm parsing, an array or an object, I first parse out that open parens. In this case, that's like our radon. We parse out the radon element. We increment our counter. And we know we're going to expect an argon element at the end. So when we do that expect, where's our parse object? When we do that expect, then we also increase the count. And then we recursively parse key values. In this case, whatever's inside the radon, I don't know what we're parsing it as. So maybe I have to squint at this puzzle a little bit longer. We're parsing it as, I don't know, filler, as another molecule. This is just how we parse molecules in general. So like looking at this, if we're doing this top down, we see CRN, and we try to parse by one of these rules. And how do you parse something as an F? Well, we follow, we go down the road and keep following these rules. So we attempt to parse that, and if not, we backtrack. So in this case, we didn't really have to backtrack. So our parser has to be a little bit smarter than the JSON parser. But I think that works. And maybe finally I'll just write my own parser combinator library and use it here. I could translate all these into like actual rules or something. But it does feel like a problem to sleep on. We are past my bedtime, and I think it's time to get well-deserved rest for all of us. But let me see. So you asked him if Avenue Code were an airport, how many runways would it have? And he gave an extremely thorough answer. Since runways are based on magnetic headings, and at the North Pole you're facing all directions, it's sort of infinite. That's a good number of runways. Oh, yeah, that is actually kind of smart, aren't they? I forget the number scheme. All right. Well, why don't we see who else is still finishing up admin code? I imagine there might be someone doing like a day 10 still, or just starting off on day 12. So Twitch. Let me expand the search a little bit. JS Dev, AOC 2025 in Rust. I don't think I've rated JS Dev yet. Are some of you familiar? And is it English? It is English. Shape. Still working on day 12. They haven't thought to do the dumb easy answer yet. Howling Fan Todd's is doing AOC, but not day 12. Okay. Let me take a look at that. Howling Fan Todd's _ Is this someone you know? It is another name that's new to me.
Thing ever. Like, I'm kind of used to it now, but like that first week or two, oh my god. You could always just do while true and move the condition to the end of the function, breaks if it fails. Yeah, while true is what I was thinking.
Okay, yeah, let's revisit some older ones.
So I could start while true, it will do it at least one time, and then I would just return it to
He
true
is
if
writing
you
in
stop.
heavily code.
Right? Because
Hilarious.
you could give me an input that requires
okay, I mean,
that's going to be ran one time,
marked,
and there's no changes that
like
you
I
can
don't know how many
that
times
can
I've
be made,
crashed
right?
my stream.
I think I would do a while
running
true.
some infinite loop.
I swear to God, I was thinking a while true. It's
That's
not
such
just
a silly
because you
problem
said
to
it.
have. I need to.
You could always just switch to a language that's actually good. True.
Okay.
That's so funny.
All right. Well,
is that
thanks,
cheating? Do you guys think it's cheating if you start part 1 in one
language,
language,
Eric,
and then you just change the language in part 2?
And yeah, I'll be doing Cinecore tomorrow night. I hope others are thinking about doing Cinecore too. And I hope you enjoy the rest of your in December.
I thought the point was to like scale your solution.
And
just use a language with.
Yeah, I think this will be the first year where I don't disappear after having a code.
Half a day done in prologue. Oh, do you? Oh, I thought you had a whole day done in prologue.
That's yet to be determined.
Multiple languages for AC? No. You can use multiple languages. I'm saying for a specific day in AOC,
yeah, as I'm figuring out
you
my
do one language
schedule,
for part 1, and then another one for part 2.
So if you want to jump in there, there's a link.
Like, I thought that you would. I thought the point of AOC was that you do it in one language, your part 1, and then you scale that solution.
All right.
So like, it kind of teaches you that when you're doing your part 1, you have to keep it like open ended on some level so you can scale it, so you don't have to like rewrite